And this video will be the first of a few on specific problem solutions for 1 and 2D kinematics for our test review. This particular problem is a good example of a ratio problem, or comparison using ratios of different quantities given some known quantity. So in this problem, an object is following some distance we call h, that I've put in quotation marks just there, after being released from rest. It takes 5 seconds for it to reach the ground. The object is released from a new height, h prime. That's what that extra little tick mark means up at the top right of the h. That straight line up there means prime, or just some new height, similar to h but different in value. And from that new height h prime, it takes 10 seconds to reach the ground. Determine the value of the new height h prime in terms of h. So you could solve this numerically. Right? Pick some numbers to go in there for find out from what height does it actually take 5 seconds to fall, and then go in and find out from what height it takes 10 seconds for an object to fall, assuming they will start from rest, and then give some ratio showing how much higher h prime is than h. Or we can use our little literal equations and our kinematic equations, or the manipulation of literal equations without substituting in numerical values to quickly get to what that ratio should be. And this is basically a ratio of h prime to h, given that we know something about how the fall height varies with time. So I've drawn a quick little picture that indicate my smaller height h. The ball will drop at some t0 and end at tf at the bottom, and that takes 5 seconds. And for the higher height h prime, it starts at some t0, ends at tf at the bottom, and it takes double that time. The double that time part, that's part of the problem. That's some given information. So note that diagram is not to scale, and one thing we have to ask ourselves is what quantities are we looking at and comparing, and that's fall time and height. And then we need to ask, what's the relationship between fall time and height? How do we know that relationship? And that's given by one of our kinematic equations and our investigations so far of dropping stuff, for instance in the acceleration due to gravity lab. And we notice that the change in the vertical position, or delta y, varies directly with t squared. And that's what that little alpha indicates here, is that varies with, or changes with. So the whole equation, once we have some constants in there and the other values, is delta y equals v naught yt minus 1/2 gt squared, or the change in vertical position equals the initial velocity in the y direction times time, minus 1/2 g, the acceleration due to gravity, times time squared, and this is assuming that down is negative. So I can notice from my problem that the object is starting from rest, it's being released, so that gets us that special little equation where the magnitude of the height is just 1/2 gt squared. And you can see there that height h, it varies with t squared, since 1/2 g is just going to be a constant value. I can write out what h prime should be, knowing that my time is going to be doubled, so I've written in 2t squared. Simplifying there, I get for h 1/2 gt squared, which is the same thing as 1 times 1/2 gt squared. That's the height value for h, or the vertical displacement of the ball when it falls 5 seconds from the height h. H prime there I simplified and solved, and that's the same as 1/2 g times 4t squared. Since it was twice the time 2t squared, I have 2 squared and then I have t squared. Together that's 4t squared. Or in other words, that's 4 times 1/2 gt squared. And that equals h prime. You can see the relationship there is 1 to 4. And so I have h prime, the new height, solved in terms of h. H prime is going to be 4 times h, or 4 times higher. I can check my answer now by using the substitution of numerical values. I already have the time values. I know what g is, and so I can solve using that the given fall time is 5 seconds, and let g be 10 meters per second squared. And I have a delta y of downward minus 125 meters. I can then substitute in and double that time, 10 seconds squared, solve for delta y, and I'll have minus 500 meters. And there you go, you see that 500 meters, that magnitude of height, is 4 times the original height of 125 meters. So that ratio works out numerically as well.